Reduction in pH value. The absorption of CO2 from the atmosphere does not affect the ocean's alkalinity. This is important to know in this context, as alkalinity is the capacity of water to resist acidification. Ocean alkalinity enhancement has been proposed as one option to add alkalinity to the ocean and therefore buffer against pH changes. Decreased calcification in marine organisms. Changes in ocean chemistry can have extensive direct and indirect effects on organisms and their habitats. One of the most important repercussions of increasing ocean acidity relates to the production of shells out of calcium carbonate, KCO3. This process is called calcification and is important to the biology and survival of a wide range of marine organisms. Calcification involves the precipitation of dissolved ions into solid KCO3 structures for many marine organisms such as coccolithophores, foraminifera, crustaceans, mollusks, etc. After they are formed, these KCO3 structures are vulnerable to dissolution unless the surrounding seawater contains saturating concentrations of carbonate ions, CO2-3. Disruption of the food chain is also a possible effect, as many marine organisms rely on calcium carbonate-based organisms at the base of the food chain for food and habitat. This can potentially have detrimental effects throughout the food web and potentially lead to a decline in availability of fish stocks, which would have an impact on human livelihoods. Decrease in saturation state. The saturation state, known as O, of seawater for a mineral, is a measure of the thermodynamic potential. Here, O is the product of the concentrations or activities of the reacting ions that form the mineral, Ca2+ and CO32, divided by the apparent solubility product at equilibrium, Ksp. That is, when the rates of precipitation and dissolution are equal. In water, dissolution boundary is formed as a result of temperature, pressure, and depth, and is known as the saturation horizon. Above this saturation horizon, O has a value greater than 1, and KCO3 does not readily dissolve. Most calcifying organisms live in such waters. Below this depth, O has a value less than 1 and KCO3 will dissolve. The carbonate compensation depth is the ocean depth at which carbonate dissolution balances the supply of carbonate to seafloor. Therefore, sediment below this depth will be void of calcium carbonate. Seeing CO2 levels and the resulting lower pH of seawater decrease. Calcium carbonate most commonly occurs in two common polymorphs, crystalline forms, aragonite and calcite. Aragonite is much more soluble than calcite, so the aragonite saturation horizon and aragonite compensation depth is always nearer to the surface than the calcite saturation horizon. This so means that those organisms that produce aragonite may be more vulnerable to changes in ocean acidity than those that produce calcite. Ocean acidification and the resulting decrease in carbonate saturation states raise the saturation horizons of both forms closer to the surface. Naxural variability in climate feedbacks at depths of 1,000s of meters in the ocean. Calcium carbonate shells begin to dissolve as increasing pressure and decreasing temperature shift the chemical equilibria, controlling calcium carbonate precipitation. The depth at which this occurs is known as the carbonate compensation depth. Ocean acidification will increase such dissolution and shallow the carbonate compensation depth on timescales of tens to hundreds of years. Ones of downwelling are being affected first. In the North Pacific and North Atlantic, saturation states are also decreasing. The depth of saturation is getting more shallow. Ocean acidification is progressing in the open ocean as the CO2 travels to deeper depth as a result of ocean mixing. In the open ocean, this causes carbonate compensation depths to become more shallow, meaning that dissolution of calcium carbonate will occur below those depths. In the North Pacific, these carbonate saturations depths are shallowing at a rate of 1 to 2 meters per year.